All right, hello everybody. Closer. Wow, this is very close. Very intimate, I like it. I can touch it? I don't want to touch it. I'm good, this is non-sterile. Anyways, good evening everybody. My name is Ethan. I came up with the worst title I could think of that still explains what's going on here. So I had ChatGPT generate it. It's called Abusing DeFi for C2, Shilling Malware in a Bull Market. Now raise your hand if you know what it's about. All right, good. That's exactly how it's planned to be. The English translation is we're going to try to use cryptocurrency as a mechanism of command and control instead of typical HTTP, FTP, whatever kind of signaling protocols you want. So with that, a few disclaimers. Views are my own, not of any of my employers, previous, and please don't actually infect people with malware. That's not good. You're not my friend. If you do, I'm a great person to be friend with. You can trust me. Trust me. All right, quick bio of me. As you can see from my many accomplishments, after the 1927 Physics Summit, I had a brief stint on Star Wars, and then that landed my job in American Idol, which is where I got really bored because those people are not good at singing. So I got into bodybuilding. So that's the most recent picture of me available. So if you need any tips on curling, I'm your guy. After that, I got into the cybersecurity field. So I actually come in from the kind of national security section. So my first professional experience with cybersecurity is coming from the Iowa Air National Guard. As a cyber operator, got a woo there from somebody who's also in the Guard in the front row. Suck up. But from there, I hopped to a company in Ames called Kingland, if anybody's ever heard of it. If you are in Ames and a student especially, it's a great opportunity, great security program over there, a lot of nice people. Great opportunity. And they make awesome shirts, which I'm still wearing, even though I don't work for them anymore. Currently, I work for Casey's with the pizzas that you guys are eating as an incident responder. So that's a little brief history of me. Once again, think the buff guy in the top left. That's me. Quick overview. We're going to go over some blockchain basics. So this talk is designed so it assumes you know nothing about blockchain and how it actually works. I mean, everyone has like the little pinch they tell people they know how blockchain. Like, I know how Bitcoin works, trust me. It's peer-to-peer. Yeah, we're going to go into actually how it works. We're going to go into Web3 and some smart contract basics. And then we're going to exploit the basic assumptions of those basics and make some C2 and do some evil. So that's fun. So let's talk about our top issues when we're a red teamer trying to run command and control, right? Our first is obviously going to be our security detections, all right? EDR, super good nowadays, doesn't go off signatures very much. It's behavioral based, super hard to get around, all right? We not only have to deal with the host side, we have to deal with the network side. Next generation firewalls is a whole smorgasbord you need to go around, all right? Attribution and traceability. People are good. Cyber threat intel people exist now, and they're good at their job, all right? They can attribute things, and especially if I'm a Russian kid, and I want to take a vacation to the Philippines, because that's apparently where all Russian kids like to go. I don't want to be arrested there, all right? I want to have my pina colada in peace. Resiliency and redundancy, all right? I want my C2 to always be available. If my C2 is not available for any amount of time, that is time that I could be skimming credit cards and ransoming networks. It's not a good sign. Also, I'm naturally lazy. I don't like to manage infrastructure. So let's try to offload that to somebody else, besides a managed service provider, because those are always bad. Don't have any managed service providers, sorry. All right, let's go over some blockchain basics real quick. So first thing that happens in a blockchain, also, in case you haven't noticed, I have a meme on basically every slide, so if you zone out from my voice or the content or you don't understand, just look at the meme. It'll all be over soon, I promise. So first that happens in a blockchain, right, is a node raises a transaction. So in the case of Bitcoin, you can think of, hey, I want to send money to Micah in the front row, who has 2 jobs at principal for security engineering opening up soon. You're welcome, Micah. All right? I package that into a block. So a block is just you can think about a blob of data, all right, that contains metadata, who it's to, who it's from, all that good stuff. And that's going to be broadcasted to all the network. Every single node on the network is going to get a copy of my block. And from there, it goes into the validation stage, right? Now, this can differ depending on what blockchain you're going to do, but they're all going to do some sort of validation. And then after they validate it, they add it to the blockchain. Once it's in the blockchain, it is immutable, cannot be changed. It is valid, and the transaction is closed. Now, we're going to focus on that fourth step right there. The transaction is validated by the nodes real quick. Actually, excuse me, we're going to do a sidebar real quick just to make sure we have a basic understanding of everything, because hashing is kind of the core of what blockchain is. You're laughing, but we need to make sure we're on the same page here. All right, hashing is a one-way function that can take any data, generally like a string or something, and turn it into completely different output. All right, it's one way, so you can't reverse it. If you have the hash, you have no idea what came into it. And also importantly, people can't, sorry, if you change even one element inside of that input, a completely different output. For example, Sam Bankman-Fried in jail, okay? See that hash, the A9? All right, now Sam Bankman-Fried, stay jail, all right? That's the E7, completely different, same concept, completely different hash, all right? And that's gonna be very important. That means it's unique, and hopefully we don't have like collisions between them where two hashes get the same, that's another thing. Anyways, consensus protocols, that was the fourth little slide back here, all right? The transaction is validated by the nodes. There's two main ways to validate that a block is actually valid. All right, we're going to have proof of work and proof of stake. Now, proof of work is generally considered an older thing. They both work great. But proof of work is what Bitcoin was originated on. And that was the original cryptocurrency. So it's the one most people think of when they think of cryptocurrencies. Okay, when they say a computer's doing math and trying to solve a math problem to figure out what's going on, that's going to be proof of work. Proof of stake, on the other hand, is a little bit newer, not super thoroughly tested on blockchains yet, but we'll get to that in a second. So let's talk about proof of stake first. Proof of stake, so you may have heard the word, like, I'm a Bitcoin miner. All right, I get a shovel and a coal mine, and I find Bitcoins in them. All right. Well, this is the opposite of that. We don't have miners in proof of stake. What we have are validators. Okay? So if you hear the word validator, think proof of stake. That's how we're validating a transaction inside the blockchain. What validators do is they stake their coins. So they put their coins up sort of like a collateral. So you can't withdraw your coins while you're staking them. You can't spend them. You can't move them. They are up in the blockchain. They're just in case you do something bad and then you lose your coins. Okay? So if you're selected, and this is on a percentile basis, so if we have a pool of 100 coins, I put up 20 coins, I have a 20% chance of being selected as the validator node. And the idea is that 20 coins is enough to keep me honest. Some problems with this include it basically keeps feeding the rich, right? If you have a lot of coins in your wallet and you have a lot to stake, there is a much higher percent chance that you can then earn more coins off those. So the rich keep getting richer and the poor keep being poor is one criticism of this. Now, this is much more energy efficient, which is why a lot of blockchains are moving to it, even despite its flaws and despite its inherent discrepancies, than our next validation method, which is proof of work. Now, this is where hashing is going to come back into. So hashers in proof of work use miners, okay? And I want to be clear, ER, not OR, okay? So they use miners. And miners guess a nonce, which is a random number, over and over again, until they get what they're looking for. Now, what are they looking for? That's a great question. They're looking for a hash that comes out of that nonce that is lower than the difficulty rating of the network currently. So the difficulty rating goes up over time, so it gets harder and harder to mine. So for example, you see there's only 3 zeros, all right, in front of the difficulty rating. That means if I take this nonce, this one-time use value, and I find a value that can then translate into a hash less than the difficulty, I have successfully found a solution to that problem. So there are actually many valid solutions to each individual block on a blockchain that has proof of work. The only question is, can you get that hash lower than the difficulty rating? So how does that work? So in the proof of, once again, we're still in proof of work here. So it takes a block header, and it chains those block headers. So block headers are full of metadata. And metadata is everything, right? It's the previous hash. It's the timestamp. It's the nonce. And remember, that's the value that the proof of work is trying to guess. And it has the hash of the previous block data. And then they are chained together in blocks. Do you get it? Yeah, thank you. I see a golf clap in the back. I'll take it. You betcha. So this is the core concept of blockchain, right? And importantly, once the guy on the left is validated, and you're on the guy to the right, you're all the way over there, 2 blocks ahead, there is no mathematical way that you can convince the rest of the network that there is an invalid transaction there. It has already been validated mathematically, everyone has accepted it, and there's been blocks built on top of it. So if one domino falls in a hash chain, they all fall. And those of you who have taken a formal education in computer science might also recognize this as a hash chain or a Merkle tree. It's the same thing. So that was invented in the 70s by a guy named something Merkle. I don't remember the last name, first name. Not important. But the innovation of Bitcoin was to take that, decentralize it, and put it peer-to-peer. So everything already existed. They just put it into place and sent it off its way. So let's talk about Web 3. And there are some promises there. It's supposed to be open, trustless, and distributed. And I got this from like a Web 3 advertisement website. So this is exactly what it says. And all of those are true, but they're actually not true, really, in practice. They're true in theory, but they all have their own individual little points of failures that bring us to it. So why not us be a point of failure, right? So let's talk about some DeFi key terms. Now, DeFi can also be equivalent to Web 3. All right? This was pioneered by the Ethereum blockchain, if anybody's ever heard of Ethereum. And Ethereum's big innovation was smart contracts. Okay, you might have heard that. Smart! They know what they're doing. It's AI. It's taking over. But they're actually not. You can read that on the slide if you want. That definition sucks. I got it off like a Webster or something. All right? Smart contracts, all they are, it's just like a class put in the cloud. It's just full of functions. That's all it does. It's a wallet that's full of functions. Okay? And those functions run on something called the EVM, or the Ethereum Virtual Machine, just like the Java one. We know that works. So good going here. Now, in order to actually compute those, instead of having AWS credits or GCP credits or, God forbid, Azure credits, right? We have something called gas, and gas makes it go. Do you get it? It's funny, right? They're funny. I thought it was funny. And gas is measured in Gwei, which is 1/1000th of an Ethereum ether. Okay? So we're talking in, it's also called a nano ether. Those who say it are correct, but wrong. So Gwei is 1/1000th. So I think currently, in order to process transactions, like 15 Gwei, so 15/1000th of a ether to process a transaction. And those can go up and down depending on the demand. All right, let's talk about how the EVM works. Got it? Everybody got it? Okay. Now let's actually talk about how the EVM works. Okay? So the EVM has 2 main components that I want to point your attention to. It's the EVM code, which you'll see at the bottom of it, the keyword immutable. Do we know what immutable means? Okay, I'm getting some head nods and some volunteers. It was a rhetorical question, but I appreciate it. So immutable means it cannot be changed no matter what. This exists no matter what you do. This will always exist. As long as the blockchain is running, this code exists. Now, machine state, where we actually process the smart contract, is volatile. That means it goes away after every transaction. So it's basically the compute. So EVMs are Turing complete, which means you can run any amount of code on it if you'd like. I would not recommend it because it's going to cost you everything. So So let's look at the actual code of a smart contract, because I can sit up here all day and I can say, smart contracts are actually simple. It's just big words made to scare you into not investigating people for fraud. But let's actually see a smart contract, all right? This is a very simple smart contract, all right? It just, as you can see at the top, says contract token exchange. What do we think it does? Thank you, Craig. Everyone else, jeez, get on his level. It says at the top, the answer's on the screen. All right. You'll see a mapping from address to units, and you can think of that if you've ever done any sort of programming before. It's just a variable. Or even if you haven't done programming before, it's a variable. X equals balances, okay? And the balances is whatever the transaction has. Now, we don't actually need to understand this for itself, because we're going to build our own here in a second. But we are going to see that it has functions, it has a contract name, it has primitives, strings, ints, everything like that. All right, everything that us IT people are used to. That's all it is. Web3 is not scary. It's meant to confuse you so you don't investigate them for fraud. All right. So now what are we trying to do with this? We're just trying to tunnel through Ethereum, right? Essentially. We're trying to create a GRE tunnel, an IPsec tunnel, some sort of tunnel through the Ethereum blockchain. All right, so we got our master hacker on the left. He's out there hacking away. He just wants to get to Harold, okay? And he wants the Ethereum virtual machine to be the middleman. So what do we need in our C2 to get this to actually work? This one isn't rhetorical. Code. That's true. We do need code. I like it. I'm looking for a really stupid answer here. Bits. We need bits to go through the internet. All right, good. That works. All right, we need bits to go through the internet to talk to malware, right? All right, so let's make bits talk through the internet. All right, we're going to make our own contract, all right? And we're going to name it, this is a malware, because guess what? It's immutable. They can't change it. Once it's on there, it doesn't care. I can say, this contract is malicious. What are they going to do? Call the cops? And what are the cops going to do? Nothing. That's the best part about this, the middle finger while you're running your C2. All right, and then we're going to add some other stuff to it. All right, so we got the contract name. This is a malware, all right? Now, the first thing we're going to do is we're going to create an address variable. Now, this is a special address variable in Solidity. And Solidity is the language that creates smart contracts, all right? It's completely object-oriented. It is Turing-complete. You can run anything on it. But it does have some special little quirks. So address stores an Ethereum address, okay? Very straightforward. Now, we're going to see a special thing called the constructor here. A constructor, very importantly, is run as the contract is made once and only once. So what this line of code does is it says, hey, whoever makes this contract, set them to the address malware owner. Now we can prove that whoever has that address malware owner, whoever deployed this contract, is that address. Is everyone following? I'm going to see some head shakes. I haven't seen any no's, so that's good. We're going to keep going. All right, now let's write some functions to interact with the smart contract with, right? So previously you saw, deposit, all right, and transfer. Well, how about victim function and operator function, right? So for the victim function, we want anybody to be able to do this. Anybody can be a victim, guys, okay? So anybody can call this function emit function. It's going to take in a string, if you're familiar with programming. I know it's a little bit small up there. I apologize. But it's going to take a string as an input. So anything we put in there can be an input. And it's going to emit a victim message. Now, you can think of emit, and like I said, Web3 people like to change the names of things for no reason, to confuse you. A Merkle tree that's distributed? No. Let's call it a blockchain, all right? It's so dumb. Transaction fees? No. It's gas, All right, so emit means log. That's all it means. So it means log to this address, okay? So the victim message we're going to make in a second. But victim message is basically a place to log whatever that function took in, all right? And then we're going to have a function operator function. And it's going to be pretty much the same thing. We're going to emit an operator message, right? But we're going to have this cool thing called require. And require is going to have some parameters. It's going to say message sender equals malware operator. So that means only the person who made this contract that we already set as a malware operator can use this function. If you are not the malware operator, this function terminates, does not work, and responds to the message. Only Russian teenagers can use this, okay? Because only for them. It's not for you. Keep your grubby little hands. You can have your own smart contracts, all right? And then finally, we're just going to put a space to put those logs, right? They're called events. And events, you can just think of namespaces, essentially. They're just little variables to store things. And on the back end, we can actually subscribe to them. So anytime there's a new event that's emitted, we can grab it, okay? So that's it. That's the whole thing. It's 25 lines of code. The vast majority of those are spaces. And we have an immutable command and control, all right? But here's the problem. The FBI, CIA, and the police can see the Ethereum blockchain. We don't necessarily want them to be able to see the whole thing, right? We just want them, if they want to know it's malware, that's fine, but I don't want them to see communications between the victim and me. All right, they're going to gain threat intel. Sometimes I'm like exfilling something juicy. All right, we want to give these guys a hard time. All right, their job is too easy, so we want to make it hard for them. So we're going to do something that's done for time immemorial. All right, we're going to do what's called a key exchange. So a key exchange is a fairly straightforward process. If you've done like any CISP learning or like any cybersecurity certs, you probably touched on these a little bit. But basically what's going to happen is, first thing, Harold, the victim, all right, he's on the green side, is going to say, hello, I am Harold. I have been infected. Here's my public key. I suggest we communicate using the key another goddamn Jira critical bug. Okay? And then their attacker is going to respond, hello, Harold. Sounds good. Let's do that. And he's going to say, great, going to use that from now on. And he's going to ask if you're up. But that's just Harold. He's lonely, all right? He's working through some stuff. But importantly to note, a public key can be distributed with the malware. So a hacker can generate a public key and distribute it with the malware. So as soon as it loads, all right, is that good? Is this good still? Okay, cool. So as soon as this malware loads, it's going to use that public key, and that can be distributed to everybody. You can think of a public key as a lock that you can distribute to somebody. You can say, hey, you need to send me a secret message. Here's a lock for it, and I have the key for it. So you can put whatever message you want in a box and use that little padlock, and then give me the box. And I was the only one who had the key. So no matter if anybody else gets the box, it's still locked. You can't open it. Only me with the private key can. So I can give unlimited locks to unlimited heralds, all right, all over the place. They can be prancing around in the meadows with locks, and it doesn't matter, all right, because only I have the key. And in reverse, I'm going to give Harold a public key just for this communication, a public lockbox, and we're going to use that for the key exchange. So just to be clear, this is a novel technique, which means it's undetected currently. This is anonymous, which means it's unattributable at the moment. This is distributed and not on our infrastructure. That means it's resilient. This is immutable and therefore unremovable. Now, importantly, one of the main drawbacks about this is that it does cost transaction fees to use. But luckily, we have all these guys. Who are they? I don't know either, and you don't. But they all use the Ethereum virtual machine as the backend. So a lot of people thought the EVM was a great product, all right? It can create contracts, classes, functions, all that stuff. Let's just steal it and make our own. Some of these, like Avalanche in particular, prides itself on being low gas fee. You know what I hear for that? Free malware. So the question is this something to actually be worried about? I mean, we just wrote a C2 in 14 lines of code that can be used by an unlimited amount of people for an unlimited amount of time, and there's nothing they can do about it unless they start their own blockchain, all right, with blackjack and hookers or whatever, right? There's nothing they can do about it. Well, this has already been done in the wild. Slightly different from the technique that we've used today, but it's been done. So Bitcoin in particular has been used as a fallback command and control for a lot of malware that basically gives the domain back when it uses Bitcoin. All right, that one's a little bit more computationally expensive and a little more expensive than the way we did it here. But they're still aware of this technique. This is not new. Additionally, there's two GitHubs that have basically the same code in it that I just presented. We all came to the same conclusion, and that is available to use if you guys would like. And importantly, I'd like to focus on that last headline, Crypto and Money Laundering, an Inconvenient Truth. Now, what that article says is that crypto is no longer the anonymous thing it used to be, right? It used to be this amorphous, what is cryptocurrency? It's lost in the blockchain. I can't track it. It goes everywhere. Tumblr's guy. Well, now we have companies like Chainalysis that are very good at determining where Bitcoin comes from and where Bitcoin goes to. They can do the same thing with Ethereum. They can do the same thing with pretty much any other cryptocurrency. All right. It is hard to get money, fiat currency, US dollars, real things, out of crypto nowadays, especially if you got them illegally. So what I suspect might happen is a lot of these places, North Korea, that are sitting on a bunch of crypto that have nothing to do with it, they're going to start selling it on the cheap, exclusively to be used essentially as cloud computing funds, right? As C2. And who wouldn't? If a Russian teenager gives you $100 worth of Steam gift cards for $1,000 worth of Ether that you can't get out, that's a no-brainer. You can't get it out. It's useless to you, right? So that's the way I think it's going. Anyway, some drawbacks and limitations. Gas fees we've already hit on, okay? They're going to be expensive. I think to run this contract, to set it up, it's like $1.50 right now. And to run a transaction, it's like 80 cents last time I checked, which is like, for C2, it's kind of expensive, right? So it's not designed to be a major thing. Yep. Set an event, exactly. So call a function or basically use it at how it's intended. Now that can be variable, right? It depends how much data you're processing through. Just like a cloud computing, it's based on how much you make it work. Okay? If you make it work less, it's less expensive, right? But also, as we've touched on before, not all EVM compatible blockchains are Ethereum. Some of them cost literally like 0.0002 cents to deploy that contract. So another point is that it's open. It's able to be seen by everybody. So unless you, on the back end, put in some computation like we did to exchange keys and encrypt it, it's going to be available to anybody to see. And evidence is also immutable. So if at one point, after we discover fusion, that we can actually use quantum computers and break blockchains and turn them into nothing, or back into nothing, I should say, that is all on the blockchain. They know exactly what you did, even if you encrypted it. All right? It's not real time. It takes a long time for transactions to go through the network. At the moment, it takes anywhere from 60 to 95 seconds on average to make it through the Ethereum blockchain. So this is not going to be something you're going to be streaming data from. You're not going to be remote desktoping. All right? You're not going to be looking at live feeds. This is meant primarily as a text-based, send a command to your malware. The malware does something, sends you the results back. All right? And another huge one is this requires connection to a blockchain. So there's one of three ways you can connect to a blockchain. The first one is a traditional one, which is where you sync the entire blockchain. And I don't know if you guys have seen the blockchain sizes nowadays, but they are gigabytes of data. And that is going to be seen on EDR. All right? If you are just downloading gigabytes of data from peer-to-peer places, that's a huge red flag. You're going to get caught immediately. The second way to do it is through a middleman. So this can be exchanges, these can be brokers, but basically a lot of people allow you to actually interact with the blockchain through them, through an API. Okay? This could be a pretty easy one because you could also hide that with HTTP traffic. The third one, Ethereum just came out with what's called a light client, which only syncs the last 1.5 days of Ethereum transactions. That one's only like 20 megabytes-ish at the moment. That does go out to a bunch of validator nodes that are certified. Hey, look at that. We got some trust back in there into a trustless system. Crazy how real world works. But it basically goes out to one of these 501 different validator nodes, says, hey, give me the last 1.5 days of transactions, and considers it self-synced. So you can do that as well. Defense techniques for defenders, all right? Because we're all blue team here-ish, mostly. At least we're not trying to do anything illegal. Blockchain access, block access to any peer-to-peer networks from your network. I mean, that's pretty 101, right? Block access to blockchain exchanges and brokers. So that's one that people aren't doing right there. And I actually want to hit that a little bit harder because it's actually really interesting. Some next generation firewalls, so think like Palo Altos, Cisco ASAs, things like that, do deep packet inspection. So deep packet inspections, when they actually dive in, they break the encryption, they look what's in the contents, and they inspect it there. What's interesting is a lot of these blockchain brokers are actually marked as finance. And that's an important caveat because most of those refuse to do break and inspect on financial transactions, similar to health transactions. There's laws surrounding it so that they actually can't do that. So what ends up happening potentially is that you can go through a financial institution, a legitimate one, for your command and control. And Palo Alto, Cisco, F5, God bless, is just not going to see that. It's not going to break and inspect it. It's going to say, that is not in my purview. You're good to go. And that's a huge vulnerability. So some of them also do a separate blockchain or crypto section. So recommend blocking all of those. But the financial ones, there's really nothing you can do, honestly, except report it to your vendor and get it classified properly. And then general hygiene, EDR, phishing, that's how these things are going to come in. That's what we all know. Anyways, questions or funny jokes you overheard at the bar? Interested in both? Yes?
Hypothetically speaking, could you see somebody using that to push out a series of hashes and get them decrypted on a remote machine and have the results sent back to them?
So his question was, hypothetically speaking, could you see somebody pushing out a bunch of hashes via this method of C2 onto a bunch of different machines and using their, I assume, GPUs to try to crack those hashes? Absolutely. I think that's a great method for it because that will use all those GPUs up, and you will pay none of the cloud computing costs. That'll be like $2 of transactions if you have a lot of slaves or victims. Sorry. Anybody else? Cool. If you disagreed or want to actually anything with me later, I'll be out in the parking lot fighting. So thanks.